Can you hear and see me? Okay.
Yes.
Yes.
Okay. So I want to finish chapter 12 today and start chapter 13. First, are there any questions or concerns?
When is, so I did one of the homeworks. When is the quiz for this chapter and the homework due? Today, tonight?
Let me look, because I don't know.
No, it's on the 10.
It's on the 10th because I pushed it back.
Okay, thank you.
You're welcome. Yeah, I thought Toyin was right. I thought I remember I pushed it back. Okay. So looking at okay. We will see that chapters are going to start going faster as we go. So synaptic transmission. Neurotransmitters can be excitatory, they can be inhibitory. It's not specifically one transmitter is not always excitatory or always inhibitory. It's the receptor that they bind to that governs what the effect is going to be. So different types of receptors are always excitatory or inhibitory, but one receptor that's excitatory will bind to a neurotransmitter. Let me say this differently. One receptor that binds to a neurotransmitter can be excitatory. Another receptor that binds that same neurotransmitter can be inhibitory. So the receptor is what's going to dictate the function or what's going to occur once a neurotransmitter binds. So acetylcholine, for example, is a common neurotransmitter that's released by many peripheral nervous system neurons. It's excitatory at neuromuscular junctions. So where the nervous system is going to synapse on a muscle. But it's inhibitory at other synapses. And there's multiple receptor types for each type of transmitter. So what goes on in a synapse? So an action potential arrives via the axon at the axon terminal. When the action potential reaches the axon terminal, it's going to open calcium voltage sensitive channels. And calcium is going to enter the terminal and trigger the exocytosis of vesicles containing the neurotransmitter, which in this case is acetylcholine. Remember what exocytosis means. What does exocytosis mean?
Exiting of the cell.
Yeah, so it's something that's going to lead, it's a substance, vesicle is going to fuse with the membrane and excrete the substances, meaning the neurotransmitter in this case, into the synaptic cleft. The vesicles will then recycle back into the cell cytoplasm and be refilled by more neurotransmitter. Once the neurotransmitters in the synaptic cleft, it's going to diffuse across the synaptic cleft and bind to ligand-gated channels on the postsynaptic neuron. So these are mechanically gated channels, or no, let me say it differently, ligand-gated channels that are going to be opened in response to neurotransmitter binding to them. So in this case, the neurotransmitter is a ligand that's going to open the ligand-gated channels. As sodium enters, it's going to depolarize the plasma membrane, producing a local postsynaptic potential. If that postsynaptic potential voltage shift is strong enough and persistent enough, it will open more voltage, it will open voltage gated channels that will then induce an action potential. So action potential comes down the axon. Once it reaches the axon terminal, it's going to open voltage sensitive calcium channels. Calcium is going when calcium infuses the axon terminal, enters axon terminal, it's going to activate the exocytosis of the vesicles containing the neurotransmitter. And therefore the neurotransmitter at that point is going to enter the synaptic cleft. Neurotransmitter is going to diffuse across the cleft and bind to the receptors on the postsynaptic neuron. If their excitatory channel gates, sodium is going to be able to enter the postsynaptic neuron and cause an excitatory postsynaptic potential. Have questions for me so far? During the events involved in an information transfer across the chemical synapse, which of the following steps would be directly interrupted by exposing a neuron to a calcium channel blocker? What would you say? During the events involved in an information transfer across the chemical synapse, so this would be release of neurotransmitter, which of the following steps would be directly interrupted by exposing a neuron to a calcium channel blocker? Calcium is involved in the exocytosis of the neurotransmitter. Here. So it binds to the vesicles containing the neurotransmitter to release the neurotransmitter into the synaptic cleft. So the answer is A. If you block the calcium from coming into the cell, you're going to block exocytosis of the neurotransmitter. Synapses are key when it comes to understanding why some drugs have their effects. Most drugs have their effects, because drugs can modify the effects of neurotransmitters. They can stimulate or inhibit the synthesis of a neurotransmitter. They can enhance or block the release of a neurotransmitter. They can activate or block receptors that bind to the neurotransmitter. They can stimulate or inhibit the removal of neurotransmitter from the synaptic cleft. So they can cause the neurotransmitter to be removed from the synaptic cleft faster, or keep it around in the synaptic cleft longer. For example, nicotine, probably the most addictive legal drug that's available on the market right now. It works on acetylcholine receptors. It's similar in its structure to acetylcholine. And it binds acetylcholine. For that reason, it binds acetylcholine receptors. And initiates an effect that normally acetylcholine would initiate. Remember how it's excitatory at a lot of neurons because acetylcholine, and inhibitory at neuromuscular junctions. So what happens is it binds to the acetylcholine receptors and activates action potentials that result in the increased release of the neurotransmitter dopamine, which is your, works most often as, bear with me here, a motion stabilizer neurotransmitter. So you release more and more dopamine into the environment. You've heard of people that nicotine is next to heroin in its addiction in its potency for addiction. For this reason, it increases dopamine release from neurons. We'll talk when we talk later about the autonomic nervous system. We'll talk about nicotinic receptors. Well, guess where they got their name? Because those are receptors that bind nicotine. Those same nicotinic receptors bind acetylcholine. In contrast to acetylcholine excitatory adrenergic synapses, inhibitory GABAergic synapses employ GABA and gamma aminobutyric acid that works, but the receptor is a gated chloride channel. What does chloride do? Chloride works to hyperpolarize the membranes. So it's going to reduce the firing of action potentials. It has an inhibitory postsynaptic potential. So when chloride enters a cell, because GABA binds to its receptor, the cell becomes more negative than the resting membrane potential. And the result is that the neuron is less likely to fire an action potential. Remember, if a cell becomes more hyperpolarized, it's more negative than it was before, meaning it's less inclined to actually reach the threshold potential and fire an action potential. Another example, excitatory adrenergic. Think of adrenaline. This is the receptor that binds the neurotransmitter adrenaline, or norepinephrine. So these receptors are going to employ norepinephrine or noradrenaline and other monoamines and neuropeptides. And that rather than opening ion channels, voltage sensitive ion channels, they are going to act through second messenger systems such as cyclic AMP. If you remember, we talked about cyclic AMP, the very end of chapter 2, because it's involved in second messenger systems. So it's involved in activating signaling cascades. The receptor that binds to norepinephrine or monoamines or neuropeptides is a G protein coupled receptor instead of an ionized channel. So neurotransmitter receptor binds to a ligand. The ligand, when it binds, activates the G protein that's attached to this receptor. This G protein then goes along and activates an enzyme called adenylate cyclase, which converts adenosine triphosphate to cyclic adenosine monophosphate, or cyclic AMP. Cyclic AMP then goes on to have multiple effects, including enzyme activation, changes in gene expression, and opening more ligand-gated ion channels. So unstimulated receptors coupled to a G protein. The binding of the neurotransmitter, norepinephrine, NE means norepinephrine, causes the dissociation of the G protein that then goes and binds to adenylate cyclase and activates it. Adenylate cyclase then catalyzes the conversion of adenosine triphosphate to cyclic adenosine monophosphate. Cyclic AMP or cyclic adenosine monophosphate then will induce several different effects, such as opening internal ligand-gated channels, activating multiple cytoplasmic enzymes, and inducing the transcription of genes that encode enzymes that can result in other metabolic changes. Although this excitatory adrenergic, you can see there's a lot more steps here. Even though this excitatory adrenergic receptor works a little slower because there's more steps involved, it works by signal amplification. So one neurotransmitter molecule like norepinephrine can result in the formation of multiple cyclic AMPs that then go on to do multiple and activate multiple signaling cascades. So these synapses are involved in signal amplification. Questions? One thing that's very important here is we like neurotransmitters. We really like neurotransmitters. They're really important. However, we need to be able to get rid of them when we need to get rid of them. Well, how do we get rid of them? We need, we want them to be here in the synaptic cleft so we can allow this next neuron to do whatever it's going to do. But we also want to be able to do other things later. So we need to get rid of the neurotransmitter. We get rid of it by having it degrade. We have enzymes that specifically degrade neurotransmitters like acetylcholinesterase, which breaks down acetylcholine. We allow neurotransmitters to be reuptaked into the presynaptic neuron, or broken parts to be retaken up. Or the neurotransmitter can just diffuse away out of the synaptic cleft. So it's either it's degraded, it can be reabsorbed, or it can diffuse away. Now, if you remember, we talked about the fact that many drugs work on the effects of neurotransmitters. One of the ways that they work on it is preventing breakdown of neurotransmitter or getting rid of it faster. Prozac is a selective serotonin reuptake inhibitor. What that means is that Prozac works to block reuptake of serotonin into the presynaptic cell. Prozac is a great antidepressant and great anti-anxiety med because it allows for serotonin to stay in the synaptic cleft longer. People who take Prozac either are not secreting enough serotonin or it's being removed too fast. So you fix this by keeping it around in the cleft a little longer. By blocking its reuptake. Questions? Neuromodulators. Neuromodulators are molecules that are secreted by neurons that have a long-term effect on entire groups of neurons rather than quick effects on a few neurotransmitters. They function in increasing the release of neurotransmitter by presynaptic neurons and adjusting the sensitivity of a postsynaptic neuron to neurotransmitters, or altering the rate of neurotransmitter reuptake or breakdown, just like Prozac would work at, be a neuromodulator. Because it alters the rate of neurotransmitter reuptake. Nitric oxide is an example of a neuromodulator. That is a gas that diffuses into postsynaptic cells and activates second messenger systems. So this is cyclic AMP. It relaxes a smooth muscle to dilate small arteries and increase blood flow. This is why Viagra works so well. Neuropeptides such as enkephalins or endorphins are neuromodulators that can inhibit spinal neurons from transmitting pain signals to the brain. Don't know if I shared this story or not. I like to exercise. That's kind of my way of balancing my life. I try at least once a week to work out for a little while. That's been my goal this semester. I can't say I always do it, but I'm trying. Because it tends to be a calming effect for me, and it tends to help me stabilize my emotions and focus a little bit. And sometimes I come up with really great ideas about what's going on with what I could improve with my teaching. In particular classes, what am I struggling with and how can I fix it? Because these are the neuromodulators are enhancing synaptic actions. Endorphins are really good at inhibiting pain. I don't do it so much now because I found out I have a curve in my lower spine, so I don't tend to be a big runner. But I like to cycle, so that's what I tend to do now. But I used to like to run. And I remember at one point I was in the very northern, right up against the Canada border at a national forest in Minnesota. And I was running along a trail. And I got back to my cabin and took off my shoe and realized that my whole shoe and sock was soaked in blood. Because while I'd been out running, one of my toenails had cut one of my toes. And I didn't feel anything until I got back to my cabin. So that's an endorphin inhibiting a spinal pain signals. Yeah, I thought I'll never forget that. I saw the blood like coming through the top of my shoe. And that's when I pulled off my shoe and realized that I'd been bleeding for a lot of the time I had been out running. So other neuromodulators, go ahead, sorry.
No, it's okay. Isn't that kind of like, it's not really pain, but like you work out, you feel good, and then the next day you're sore? Like, is it kind of along those lines too? Or is that something completely different?
I think you're sore because you're tearing your muscles, which is part of exercise, is to tear your muscles. I think it makes you sore because you tear your muscles, but I think you're right, the endorphins kind of cover that. But people who weight lift are constantly reconstructing their muscle. They tear it and it builds up. So I'm guessing that's also why you're sore. And sometimes you get back from an exercise routine and realize you're sore. And it's you're right, it's usually worse the next day.
Yeah.
So other neuromodulators are hormones and neurotransmitters like dopamine, serotonin, and histamine. What this means overall, this last statement, is that a neurotransmitter, hormone, or neuromodulator are not defined by the chemical itself. One given chemical is not only a neurotransmitter, only a neuromodulator, only a hormone. It can play multiple roles based on the context. So one neurotransmitter can be a neuromodulator in a given situation. Last part of this chapter, talking about neural integration. Neural integration is the ability for a given neuron to receive multiple signals and process the information and make a decision about how to act. So the more synapses a neuron has, the greater its information processing abilities. A pyramidal cell in the cerebral cortex can have about 40,000 synaptic contacts with other neurons. Remember in the cerebellum, I think this was an earlier slide, can have up to 100,000 synapses with other neurons. So neural integration is the neuron's ability to process information, store and recall it, and make decisions. This integration is based on the potentials received at the axon terminals, at the axon's trigger zone. Well, how do we perform this neural integration with these postsynaptic potentials? We have excitatory postsynaptic potentials, and we have inhibitory postsynaptic potentials. Remember when we talked about action potentials, we have to get to a certain potential. We start at -70, and we have to reach threshold to fire an action potential. That's only going to get fired at the trigger zone. So the rest of the neuron, like the dendrites and the soma, are going to be receiving have multiple synapses that can result in a combination of excitatory postsynaptic potentials, where the membrane becomes less negative, meaning it gets depolarized, or it can have inhibitory postsynaptic potentials, where the membrane becomes even more negative, meaning it's farther away from threshold. Sodium flowing into the cell is going to make the cell less negative, meaning it's going to be depolarized, meaning it's going to move closer towards threshold. An inhibitory postsynaptic potential means that it's going to become more negative. Either chloride is going to move into the cell or potassium is going to move out, resulting in the inside of the cell becoming more negative. These are local potentials, both of these. And remember that local potentials can sum. So a given excitatory postsynaptic potential or one inhibitory postsynaptic potential is not going to dictate whether a neuron will fire an action potential, but it will change the rate of firing by stimulating or inhibiting the production of action potentials. So an inhibitory postsynaptic potential is going to make the inside of the cell more negative than it was before. So resting membrane potential is -70. An inhibitory postsynaptic potential is going to make it maybe, let's say, -75. It's going to make it more negative. We have to reach -55 to fire an action potential. So the further we get away from -55, the less likely we are to fire an action potential. So if potassium leaves the cell is going to become more negative, meaning this is going to be an inhibitory postsynaptic potential. If chlorine starts entering the cell, which is negatively charged, the inside of the cell is going to become more negative, meaning further away from threshold. If sodium enters the cell, the inside of the cell is going to become more positive, meaning it's going to get closer to reaching threshold. So inhibitory postsynaptic potentials are going to hyperpolarize the membrane. Excitatory postsynaptic potentials are going to depolarize it.
So sodium and potassium are negative, right? Or I'm sorry, potassium and chloride are negative, and then sodium is positive.
You're the opposite. Potassium and sodium are positive, chlorine is negative.
Potassium, sodium. Okay, but I'm saying like when they enter the cell. So the potassium will make it more negative, the chloride will make it more negative, and then the sodium will make it positive.
Right.
Okay.
Yes, you're right. Because if potassium is leaving the cell, it means that positive charges are leaving the cell. It's just going to make it more negative. If chlorine is entering the cell, because it's got a negative charge, it's going to make the inside of the cell more negative. If sodium enters the cell, because it's positively charged, it's going to make the cell more positive.
Makes sense.
Yep. Normally, a single excitatory postsynaptic potential cannot initiate a nerve impulse. Remember, these are decremental. These inhibitory postsynaptic potentials, they're decremental, meaning they are reversible and they decrease the further away from the origin. Summation is a process by which we add up postsynaptic potentials. And can possibly activate an action potential. I'm going to stop just for a second here. Give you an example of summation. So I have some inhibitory postsynaptic potentials that make the inside of the cell more negative. I have some excitatory postsynaptic potentials that make it more positive. One given postsynaptic potential is not going to activate an action potential, most likely. It's going to be a summation of them. One adding its effects to another. So an inhibitory and an excitatory postsynaptic potential can neutralize one another. A negative added to a positive is going to neutralize. Two positives are going to make the overall cell more positive. So neural integration is a summation of these different potentials. So I have to reach, I'm at a -70, and I have to reach a -55 in order to fire an action potential. I'm at a -70. The first potential that, the first signal that I get is a +5. Which then because I add 5, that puts me at a -65, right? If I add 5 to -70, I'm now at a -65. So I'm closer to threshold. If you add 5 to -70, I'm now at a -65. So we're adding positive and negative numbers together here. I'm at a -65. My next one that I get is a -10. So now I was at -65 before, but then I got a -10. So now I'm at a -50, a -75. So now I'm farther away from threshold. Then I get a +7, which then puts me at I have to remember, a -67. Then I get a -5. And so now I'm at a -72. So I'm a little tired, so I'm struggling to add up things today. -72. Then I get another +10. So now I'm at a -62. And then I get a I get a +12. I get a +12. I'm now at a -50, which means that I've passed threshold. So I've reached a threshold value and I fire an action potential. But until I reach a -55, which means each one of these, this would be an excitatory, this would be an excitatory postsynaptic potential. This would be inhibitory. This would be excitatory. This would be inhibitory. This would be excitatory. This would be excitatory. And until I reach this value or above it, I'm not going to fire an action potential. That's summation. That's the way a neuron disintegrates information. Questions? So multiple excitatory inhibitory come in and they get summed together. And if the membrane potential reaches a -55, an action potential will be fired. But until that value reaches a -55, no action potential is fired. Two modes by which things can be summed. Temporal summation is when one presynaptic potential is going to generate so many excitatory postsynaptic potentials that each potential comes in before the last one has faded. Remember how these are local postsynaptic potentials are local potentials. So when the stimulus stops, they stop. And they kind of just fade away. Well, what if they're coming in so fast that the next one is adding on top of the effects of the first one, because the first one hasn't had a chance to fade away yet. And they're coming in so fast via one neuron. This is temporal summation. So when all of the postsynaptic potentials from one presynaptic neuron are adding up to a voltage that reaches threshold and stimulates an action potential, that's temporal summation. Spatial summation is when the excitatory postsynaptic potentials are coming from multiple presynaptic neurons onto one postsynaptic neuron. And we reach threshold and an action potential is fired. So temporal is one presynaptic neuron firing multiple synaptic potentials or initiating multiple postsynaptic potentials. Spatial summation is multiple presynaptic neurons firing, initiating postsynaptic potentials. So suppose that the excitatory postsynaptic potentials are summating in a postsynaptic neuron in response to simultaneous summate in a postsynaptic neuron in response to the stimulation by neurotransmitters glutamate, serotonin, and acetylcholine released by 3 separate presynaptic neurons. Is this an example of spatial or temporal summation?
Wouldn't it be spatial because it's several,
You're right, it's several.
multiple?
Yep, because it's multiple presynaptic neurons. Which of the following is a true statement about neurons?
Take a guess. Is it B?
Say it one more time.
Is it B as in boy?
Why do you think that's right?
Because they're going towards the cell body to tell the cell body what to do, and then the axons release that signal.
Right, that's correct. And they only move in one direction because of the refractory periods. But yes, that's right.
I surprise myself sometimes.
That's funny. Okay. No, that's right. Membrane depolarization is caused by what?
Is it D?
D. Why do you
Is it
think
mi-
it's D?
Because it makes it more negative. No, depolarization is freezing it. It's stopping it. That's not right. Would it be B because it's disrupting it? So it's stopping it?
Is it all, is it causing, it is a disruption, but a hyperpolarization can also be a disruption. Well, you're close, but it's not B.
Could it be?
It's A, because it's the influx of sodium ions, because if sodium ions are entering the cell, it's going to make it more positive. And that's a depolarization.
So depolarization is not freezing it, I guess, for better lack of words. Like
Nope, it's just making it more, so the outside of the cell is more positive. And depolarization is essentially removing the polarity.
Gotcha.
Which of the following is not true about synapses? Someone besides Caitlin. In a minute, I'm going to call on somebody.
I'm not 100% sure, but would it be C?
Why do you think it would be C?
Well, I kind of did like process of elimination, but that was the closest one that seemed like an answer, but I wasn't 100% sure.
Let me, you're really, really close.
Okay.
But can a neurotransmitter bind to both sides of the synapse?
Not both sides.
So look at the other choices and what's another option that wouldn't include that.
Is it B as in boy?
Actually, wait. You know what? Shoot. I'm messing you up because I'm not reading it correctly. You're right on the first one.
Oh, it is C.
Yeah, because what's not true?
They
You're
can
right.
bind to both sides.
Okay,
Yeah.
and I'm so sorry. You're right.
No, it's okay.
I'm a little brain dead today for some reason. I'm so sorry. You're
I
right.
think we all are. It's okay.
Sodium potassium membranes help maintain membrane polarization by what? What do the sodium potassium pumps do? Someone look up Google for me really quick what the sodium potassium pump does.
Well, I'm pretty sure it's D or E. I just don't remember if it pumps it in or out of the cell.
You're right. It's E.
Okay.
So it's gonna pump 3 positively charged sodiums out of the cell. Remember, the concentration of sodium is higher outside of the cell, and it's lower inside of the cell. Potassium is higher inside of the cell. Good job, Brianna. That's right. Because it's going to be involved in maintaining the sodium potassium concentration gradients, because it's always pumping sodium and potassium against their gradient. Okay, almost the last part of this chapter, presynaptic facilitation. One neuron is going to enhance the effects of another neuron. Neuron F releases a neurotransmitter. This neurotransmitter allows for calcium channels on the postsynaptic neuron, which is also the presynaptic neuron, is going to increase the amount of allow for the calcium channels on another neuron to stay open longer, causing neurotransmitter to be released for a longer period. So neuron F is going to release neurotransmitter, which is going to allow for calcium channels on neuron S to be open for longer. Neuron S is synapsed with neuron R. So if neuron S allows for neurotransmitter to be released for longer, what that means is that neuron R is going to be activated for a longer period. So neuron F, the facilitating neuron, is going to accentuate or add to the be an agonist on neuron S by facilitating how long it activates neuron R. In opposition to presynaptic facilitation, presynaptic inhibition is where one presynaptic neuron is inhibiting the effects of another one. So neuron I is going to inhibit the effects of neuron S. They're often used to reduce or halt unwanted synaptic transmission. So neuron I releases an inhibitory transmitter, GABA. GABA prevents calcium channels from opening, even though an action potential reaches the axon terminal of neuron S. Neuron I is going to block the calcium channels from opening. That would normally allow for the release of calcium, assuming release of neurotransmitter. The result is that neuron S, because the calcium channels don't open, is not going to secrete neurotransmitter. So facilitation is enhancing the activities of another neuron. Presynaptic inhibition is inhibiting the actions of another neuron. last part, neural coding. This is the mode by which information about and around the body is communicated in a meaningful pattern of action potentials. We often call this what's called the label line code. The basis of this is that each nerve fiber leads from a receptor that only recognizes one form of stimulus. An example is the optic nerve that only receives, the receptors of the optic nerve only receive light stimulus. They only can receive light stimulus. So any stimulus to this nerve is perceived as some form of light. I think this is one of the coolest things in the world, because what I want you to, because I'm not wearing eye makeup yet today. We've all done this. You rub your eyes, right? Rub your eyes. Now, rubbing your eyes, push on them for a minute. What do you see? What do you see in your, what do you see? When you close your eyes and you push on them, what do you see?
Nothing.
Do you see absolutely nothing?
It's like dimmer, I guess you would
No,
say.
do it. Caitlin, do it and tell me what you see. Unless you're wearing eye makeup, I don't want you to smear your eye makeup. But do it and tell me what you see.
Like streaks of light.
Yeah. But you're not receiving any light. You're not causing a light stimulus, right? When you push on your eyes.
Mm-hmm.
But the receptor only can recognize forms of light. So what it's trying to do is the nerve is trying to respond to that pressure, but it can only respond if that stimuli is light. So it's trying to analyze that pressure stimulus as a form of light. Does that make sense? The receptor is being stimulated by pressure, but the optic nerve only recognizes signals of light. And so it's trying to interpret that as a symbol of light. And it just doesn't work very well. Because you can't do that. So a stimulus strength is interpreted by which and how many neurons are firing. Different neurons have different thresholds of excitation. A weak stimulus will excite neurons with the weakest, lowest thresholds. A stronger stimuli will excite less sensitive, high threshold neurons. As the stimulus becomes stronger, additional neurons will be recruited that have a higher threshold. So a stimulus intensity is judged by the firing frequency. A weak stimulus can cause a neuron to generate 6 action potentials per second, while a strong stimulus can generate 600 per second. So different thresholds of excitation and stimulus frequency. So strength is threshold intensity. Stimulus strength is threshold excitation. Stimulus intensity is the frequency of firing. Questions? Neural pools. Each pool is a complicated network of neurons that process specific types of information. So one given pool can consist of thousands of interneurons that are concerned with one specific body function, and multiple presynaptic neurons that are acting on one postsynaptic neuron. Some of them are excitatory, some of them are inhibitory. A diverging circuit is where one nerve fiber is going to synapse with several postsynaptic neuron cells. And each one of these will synapse with several more postsynaptic neurons. Such a circuit allows one motor neuron of the brain to ultimately stimulate thousands of muscle fibers. So one presynaptic neuron synapsing with multiple postsynaptic neurons that then go on to synapse with multiple other postsynaptic neurons. A converging circuit is where the input from many fibers is funneled to one neuron. This would be an example of a converging circuit. Multiple presynaptic neurons converging onto one postsynaptic neuron. A reverberating circuit is where neurons are stimulating each other in a linear sequence. And some neurons later in the path are putting out axon collaterals that come back and stimulate presynaptic neurons further back in the process. So one presynaptic neuron converges on a postsynaptic neuron, which converges on another neuron, which converges on another neuron. And some of the postsynaptic neurons come back and stimulate neurons further back in the process. A parallel after discharge circuit is where a single presynaptic neuron is going to stimulate a group of neurons, which then synapse with one common postsynaptic cell. Questions? I recognize that we only have 7 minutes left, but I still want to start the next chapter.
I think I might have printed out like a different PowerPoint than what you had, which is fine. But it has like the long-term memory, the short-term memory.
You know what? I cut that out.
Okay.
I cut it out. I realized, I was trying to figure out a way to save some time, and I cut that out. It's interesting material, but it isn't as important as other things.
Okay. Yep. Gotcha. I just wanted to make sure.
Yes, I apologize.
That's okay.
Yeah, I had that in there and then I thought, you know what, I'm gonna run out of time. And I thought, what can I do to save time? And that's why I took that out.
Now, will those be like on the quizzes and stuff, or you
No,
took them out
No,
completely?
I took it out
Okay.
completely.
Gotcha.
Uh, Give it a second. There it comes. So the spinal cord, spinal nerves, and somatic reflexes. Spinal cord injuries in the US. The spinal cord is this information highway that connects the brain to the lower body. However, thousands of Americans are paralyzed by spinal cord injuries every year. Why? Why are spinal cord injuries so devastating?
Because they can paralyze you.
Well, why can they paralyze you?
Because you have nerves.
That's the only
Because
thing
they're
that
nerve-
takes signals from the brain anywhere else in the body.
Right, but what, lots of cells are like that. What makes neurons different from other cells?
They communicate with each other constantly.
They
Well,
don't
that-
regenerate.
They don't regenerate. So once they're gone, a lot of, especially in the nervous system, because they don't have that neural lemma. Do you remember that from before when we talked about the regeneration of neurons? Because they don't have the neural lemma and they don't have Schwann cells, they don't regenerate. Functions of the spinal cord. The spinal cord is used in conduction. So nerve fibers within the spinal cord are conduct sensory and motor information up and down the spinal cord. They're involved in neural integration. So spinal neurons are going to receive input from multiple sources, integrate it, and execute appropriate output. We'll talk about reflexes later in this chapter too. Locomotion. The spinal cord contains central pattern generators. So these are groups of neurons that coordinate repetitive actions of contractions for walking. This is why when you learn how to walk, most often you'll never forget how to walk once you start. Once you learn how to ride a bike, you don't tend to forget. Reflexes. So the spinal cord also is key to reflexes, which are involuntary responses to stimuli that are vital to posture, coordination, and protection, maintaining homeostasis. The spinal cord is a cylinder of nervous tissue that arises from the brain stem at the foramen magnum of the skull. This is a column of nervous tissue. Within the spinal cord, there's about 100 million neurons. And there are about 50 times more neuroglia than there are neurons. So what, you're looking at about 50 trillion neurons, somewhere right in there. It extends from the medulla oblongata in the brain to the conus medullaris, which is the tip of the spinal cord. Last question for today. Spinal cord injuries commonly result from fractures of the vertebrae C5 to C6, but never from fractures of L3 to L5 vertebrae. Well, why? Why do you rarely see them of the lateral vertebrae, the lumbar vertebrae?
Is that because it's like curved in and you like you're, I don't want to say sitting, but you have more stability?
Well,
I'm
what
just
I would
guessing.
think is, first off, you have 5 lumbar vertebrae here. The lumbar region is actually probably bigger than your neck region, if you think about it. Your neck region has 7 of them. You have 8 spinal nerves, but 7 vertebrae. What does that result in with your neck? You have a lot more flexibility of your neck. You can do this with your neck. You can't do that with your lumbar region, right? Not as well. I think the more, when we talk about joints, the more flexible, the least stable. So you're more likely to have an injury sustained here than in the lumbar region. Mom, does that sound about right? Of course, she's not listening. But I think that's about right. Is because first off, they're bigger vertebrae in the lumbar region. And there's a lot more flexibility to the vertebrae in the cervical region than there are in the lumbar region. You guys have a wonderful weekend.
Thank you. You as well.
Thank you. Bye-bye.
Bye.
I apologize about yesterday. I
What?
was on
Oh, no, don't. You were
or
flying.
Tuesday. Yeah. Well, I thought the airplane Wi-Fi would work. And I don't think it had a strong enough connection. And I literally tried everything.
Well, did you see that I tried to email you the link?
Yeah, I even clicked on it and it was just spinning.
Ah,
I sat there for like 15 minutes to try to get in, and I knew that the connection must not have been strong enough. So
yeah. Oh, I'm sorry.
that's
kind of-
okay.
It stinks,
As-
but go ahead.
If it have you figured out like the posting of the recording?
have. I have.
I'll just
I
watch
will-
them.
I don't know when I'll get it posted. I'll try. I will get it posted this weekend.
Okay, yeah, that works. And I'll just go back through.
Okay.
So no worries. Thank you so much.
Are you enjoying the weather?
Yeah, it's like 75, 80s, and I don't want to come home.
I am a little jealous. Okay.
Yeah, the only I'm still jet lagged because it's almost 11 o'clock here. So it's,
Wow.
yeah, we're 3 hours behind you guys. So
Did you go for personal or business reasons?
kind of both. There's a huge car show out here. It's called SEMA. It's the biggest one in the United States, and my husband runs a car magazine, so he got
Okay.
invited to go.
Okay.
So that's really why we're down here. But I mean, we kind of like toot around and go wherever. After we have a practical coming next class, and after that, there's a real bodies museum type thing at our hotel.
Oh, that's cool.
So we're gonna go check that out. I wanted to do that. So
If they let you take pictures, take pictures.
oh yeah,
Some
I
of that
will.
stuff you'll never be able to see again.
Yeah, absolutely. I heard it was really good. So we're gonna go check that out and see what we can see and go from there.
That's awesome. Enjoy it. I'm a little
Thank-
jealous. Especially
you
if
so
the
much.
body thing. Okay,
Have a great week.
you too.
Hey, Professor.
Hi.
Sorry, I know I was supposed to be in the morning class, but my grandma had cataract
I
surgery.
wondered, but I don't care
Okay,
for which class you join. If you join this class, you join this class. I don't care.
okay. I think I'll have to do that like one more time because I have to take my sister to an appointment later this month, but normally the 9 a.m. works a lot better.
It doesn't matter to me. Don't worry about
Okay.
it.
Okay, I also just want to let you know I was here. I wasn't just skipping class
Well,
entirely.
I thought when I saw your name come up today, I thought, wait, isn't she in the earlier class? I thought, well, maybe she's not, because there's a lot of students, so I didn't think too much about it.
Okay, awesome. Yeah, I'm normally the 9:30, but yeah.
That's fine by me, Erin. It doesn't matter.
Okay, thank you.
I'll talk to you soon, okay?
All right, have a good weekend.
You too. Bye-bye.